Okay, thank you, Dr. King. I have just few slides to show this how to get the relaxation dynamic and distribution of charge as a function of the coordinate and also time out of the non-adiabatic coupling and here we consider the without a spin. Okay, so just as a spoiler, I'm going to plot this greenish and bluish figure. I just borrowed that from the Dr. Hahn paper, published, I think, 2015. So just as a review, what we have done so far, we first did some geometry optimization, getting a count car out of it, then annealing the system and doing some heating calculation, then molecular dynamic calculation. After doing molecular dynamic calculation, we did coupling calculation. And for each time step, we generated the coupling files. Previous time, we did some calculation on the couplings to get the RRR files. And today we are going to plot the relaxation dynamics. What do we need so far today to plot those greenish figure? We need a rent tensor file, RRR, energy pop file, including the orbitals and energy of the orbitals, for master optics files and band outs. So far we, or from the previous week, we have these two files, RRR and energy pop. So for this model, that was just a standalone PCBM model. I just chose 20 band gap. Maybe it's not enough, but just for the simplicity, 20 band gap near the 20 orbital near the band gap. So the first one is 147 and the latest orbital is 166. So totally we have 20 orbitals, and RRR file was calculated last week. So we need two more files for master optics and band out file. So to have these two files, actually we need to do some calculation after using the file that we have from geometry optimization. So we can copy CONCAR as a postcard into the, for instance, folder partial charge calculation, and copy the in-car file related to the partial charge calculation. And then finding for master optics and band out. This is a typo. We do not need any molecular dynamics. So this is kind of, should be partial charge calculation. Forget this one. And yeah, so to do partial charge calculation, we need the in-car file available in the bin directory. So just need to specify the range of the orbitals that was assigned previously in the energy pop. For instance, here, the range of orbital is minus 5.6, for instance, to minus 0.8. So I put that here, minus 5.9 to minus 0.6 to cover all range of the energy pop. So for each of them, we will have a partial charge file generated by this file. So after this, we need a pair file named band integrate bas5. Just need to pay attention that in the bin directory, there are several files with the same name, version 5, but I usually face some problem with them. So just this one worked as Dr. Killen suggested. So in this file, we need to edit that file via BI command. So we need to specify the first orbital and the latest orbital plus 1. So here in the energy pop, latest orbital was 166. but this value should be +1, so 165. And after running this code, Perl band integrate VAS5, when we run this code, it will give us a bandout file. So right now, after running this code and adjusting the orbitals number, code will give us the bandout file. And for master optics file, I'm using this command, oscillator strength, named chemistry 676, but I think maybe Aaron, Yulan, and Dr. Killing Group use another file. I'm not sure about that. You can check that later, but this file is available in the bin directory and works well. And after running this code, it will give us the for master EQ file that we can simply copy, that named as master optics, that is used in the Matlab file to plot this value. So to execute the Matlab file, we have a Matlab file, red field, named like this in the bin directory, and we need 4 more files in the same directory with the Matlab script, RRR, energy pop, bandouts, and for master optics. So after that, we can just adjust the value, few values in the Matlab script. So for instance, time step here, I just have the coupling files until time step 400. HOMO number, LUMO number, it's calculated based on HOMO, the first orbital in the energy pop, the latest orbital energy pop, and the total number of the orbitals that is calculated simply based on those formula. And there is 2 important parameters that are IH and IE. So they are kind of key parameters here for this calculation. So IE is index of excited electron. So it could be 1 for the LUMO, 2 for LUMO +1, and the same manner, IE is index of excited hole. And it's 1 for HOMO, 2, for instance, for HOMO -1, and so on. Sorry. So after generating those files, running those Matlab files, what happened? Okay, it will give us the actually this 2-figure distribution of charge as a function of time and energy. So as we expected, for instance, we saw that figure from Dr. Hahn paper, we expected to have a decay here, but my simulations are not done yet. The system is a little large, so I'm waiting for more time, maybe at least finishing 1000 time steps to reach that decaying value. And also this is the charge carrier dynamics versus time in the z direction of the simulation box. Also code will generate some distribution in z direction as a function of time for electrons, hole, and electron holes. Usually electrons appears at the red regions and holes concentrate at the blue regions. So also where the net distribution of this value also is negative. To be honest, I'm not pretty familiar with this kind of plots to provide more insight into them. I think just plot them 10 or 15 minutes before the meeting. So if you have any question, feel free to ask. So I may ask Dr. Killian to help to answer those questions also. Yeah, this is my last slide. Thank you.
Okay, please join me in thanking Amir for being brave and diving into deep water of new subject so enthusiastically. So, yeah, any questions are welcome. please feel free either type or ask verbally. And since we are a small group, it shouldn't be formal. Just raise your voice whenever needed. Let me add a comment. So the code works very quick, and the disclaimer that let's wait for another 2,000 time steps is not accepted. The initial values of electron and hole are selected. If you look on this table that you're showing of energies, if you excite from HOMO -1 to LUMO +1, they are degenerate with HOMO and LUMO, and then there will be not much interesting dynamics. So in order to observe something, one needs to excite to select these numbers IE and IH much bigger. Not much, but bigger. And there, maybe I can ask, to be quick, David, would you suggest any rule for selecting parameters IE and IH? And you,
First thing I usually look at is oscillator strength.
Perfect.
The higher the oscillator strength, the more likely that it's a useful excitation to look at.
Perfect. So how do you select which oscillator strength is bigger? Do you scan it with your human eyes, or you have some trick scripts?
I don't have a trick script, but I just sort it by whatever the column the oscillator strength is, and that does it all for me, so I don't have to scan with my eyes because it would take forever.
Okay, so you take those pair of orbitals which produce largest oscillator strengths, correct?
Yes.
And they are not necessarily the lowest excitation. They can be.
They're virtually never the lowest excitation.
Okay. More questions to Amir. Any questions Amir wanted to ask to himself?
No, actually, I'm good right now. So, but need to wait to finish the coupling calculation. Just one question: during the coupling, as for instance, I have 500 or 600 coupling files generated. Some of them are blank, so nothing.
No. If please contact either one who has previous history of doing these couplings. It could be myself, Dr. Hunt, Dr. Fordy, David, and blank couplings is not good. They should be non-zero, one. And second, it is not needed to have so many couplings. As soon as autocorrelation function converges with a given number of couplings, maybe 100, you can stop calculations and go forward into electron dynamics.